bit of Portuguese, so you can switch between Portuguese and English, it's okay. Obrigada por vocês terem vindo, de estar recebendo a professora Caroline. Obrigada para quem está assistindo também. Então, eu vou apresentá-la, né? A professora Caroline Gavart. She's an assistant professor at the Faculty of Geoinformation Science and Earth Observation at the University of Twente in the Netherlands. She previously obtained her PhD degree at the same university and master's degree at the University of Valencia and Lund University. She's currently member of the Dutch Young Academy of Scientists and co-chair of the International Society of Digital Work Working Group 3 on Digital Work Governance and Ethics. Caroline was one of the 15 global experts invited to review the United Nations Global Sustainable Development Report, to be released later this year. And her research focuses on responsible AI for Earth observation, with a focus on applications in low and middle income countries. Next to her academic position, she's an international consultant for the World Bank, where she advises projects using geospatial technologies and community participation. So thank you very much for being here and accept to do this little talk with us. So the stage is yours.
Thank you. So thank you for the introduction. Is it okay with the microphone like this? Can you hear me okay? Yeah? Good. If not, just raise your hand or wave. Also, I know I have a tendency to speak quickly, so if it becomes too fast, just let me know. I'm used to it. I know it's a problem. So the presentation will be in English. I think also, especially if we have a small group, to make it interactive, if you have any question along the slides, you can also just interrupt. And then if it takes, just raise your hand and we can also have questions during the presentation. The questions can be in Portuguese, I can understand a bit, and otherwise we have lots of help with the translation. So good, so today I wanted to talk about kind of three main topics. I wanted to talk a bit about how Earth observation can be used for sustainable development and humanitarian aid. I wanted to explain the importance of responsible AI, and also to give some reflections on future directions of research as I see them as well. So the Sustainable Development Goals, there are many, and in one presentation it's difficult to go into all of them. So instead of trying to explain everything about all of the Sustainable Development Goals, I thought it might be nicer to give a couple of examples from projects that I've been involved with. And so for as a bit of a background information, I don't know, I know all of you come from different studies, but so in Earth observation, what we do is Earth observation is all about getting information about the surface of the planet using different sensors at a distance. So usually it's satellites, it can also be from drones, and it can also be sometimes from the ground as well, when we think of from the Earth's surface. And we use it to monitor the changes and to see what's happening. And it is very important actually for sustainable development and disaster risk management, because we can actually see what's happening on the Earth's surface in areas that is often difficult to get data. So this is a satellite image just from Google Earth, from an area along the Nile, a bit to the north of Sudan. And you can see a very large flood event over the city. And this is, so just going back and forth, even just visually with the images, we can see how much, of course, it can mean for sustainable development. So one of the things that I work on is flood risk management. And what is one of the problems? So if we have a flood event like here, you can see that many parts are affected, many cities, different agricultural areas and services. And one of the problems is that, especially in low and middle income countries, or if we think especially in rural areas that are far from the city centers where a lot of the knowledge is concentrated, we often don't have any data. So we might see, okay, there was a flood in this region, but how many houses are actually affected? How many people are in need? How much support do you need to send them? These are all questions that Earth observation can help with a lot. So when we look at the Earth, on the one hand, why Earth observation can be so helpful is because we have different sensors that are collecting data. So you have satellites that are passing regularly, you can fly drones. And at the same time, we have artificial intelligence that can help process all of this data automatically. So if you think of satellites going around the Earth every day, with the use of artificial intelligence, and we can also help process this information faster. So for example, here what we see is a result of some work that was done by DLR, which is a World Settlement Footprint 2019. So they looked for the entire globe. They developed a data set at 10-meter resolution that shows which areas are built up, so are buildings, and which areas are not. So here we can, looking over the same area that was flooded, we can actually see in black are the areas that had buildings. So if you look at which area was flooded, even though there might not be any information about who's living in this village or not, you can actually, because we have this data over the entire globe, you can get an idea of where the buildings were. So one of the benefits of Earth observation is that you can get very accurate data, and it can be up to date. So because satellites are passing regularly, you can update which areas are built up regularly as well. And we can also go back in time. So here we see also from DLR, from the German Space Agency, what they call the World Settlement Evolution. And it also shows built up areas, but the different colors show the year in which the area was first built up. So this one runs from 1985 to 2015. The redder areas, these are different cities in Africa, but also it's a global product. So the red parts of the city are the older parts, which were first built in 1985. And as we move to yellow, green, and blue, you can see how the city is growing. So you can see which areas are growing. You can also see how fast the city is growing in spatial extent. And another thing that is very important about these types of data sets is that, as I said, I work also for the World Bank, and there it's often important to compare what's going on in different countries. But each country has a different way of collecting data, a different way of managing data, a different way of defining what is a city, what is not a city. And so global products like these from Earth observation, because they are standardized, they also help compare different regions. So also if you think about the Sustainable Development Goals and the indicators, they are also supposed to be comparable at a global level. So in a way, like, these ways of gathering statistics through Earth observation are really helpful in that they are not as dependent on the processes within the different countries. So when we have the areas exposed to flooding, you can also, or when you have the built-up areas, you can also overlay it with flood models, and then you can get ideas such as a population exposed to flooding. So here was some work done by some colleagues at the World Bank, where they compared the World Settlement Footprint of 2019, so all over the world where built-up areas are, with some global flood models, and they could count the percentage of the population that is exposed to flooding. And this is at the administrative 2 level. So it's not at the country level, but the first administrative division. So in the US it would be the states, in the Netherlands we have provinces. And here you can see the percentage of the population that's estimated to be exposed to flooding. One caveat here is that it's the population exposed to flooding without any defense measures, because there's not a global database of defense measures. And so that's why if you look very closely at my own home country of the Netherlands, we are all exposed to flooding because most of the country is actually below sea level, right? So that's one of the issues in this data set, but it helps compare what's going on. Another example of such a global product that has been used on satellite imagery is on the Global Forest Watch. I don't know if you've seen this one, but this is also, I don't know the colleagues behind this, but here what they did is they used satellite imagery over time to see where the forests are growing and where deforestation is happening. So that I zoom into Brazil, and then you can see they were comparing since 2020 or 2001 to 2021. Everything that is pink is tree cover loss. So I said that in Earth observation, we have many different types of sensors, and I thought it was interesting to talk a little bit more about the difference between satellites and drones. So one of the benefits of satellites is that they have more global coverage, whereas with drones, it's over a smaller area. So also if you are looking at a sustainable development issue at a global level or at a regional level of a very large extent, satellite imagery can be very useful because you can easily cover a very large area. Whereas if you take, for example, a drone, the area is restricted. Theoretically, if you have a lot of time and a lot of drones, you can cover a large area, but it's also a lot of data, a lot of processing, and not always very useful. One of the other differences is that satellites, because they have a regular orbit, they have regular updates for the lifespan of the satellite, but they're also fixed to certain timings. So if you look at, for example, Landsat, which is a medium resolution satellite, it circles, for example, about every 2 weeks. So if you have a flood event happening in the space and the satellite is not there, you will not see it in the satellite image. At the same time, if you have a drone, if you own it, you have a lot more control over when you fly, or what time of the day, over which area. If there's a recent flood event, you can go and you can fly over and you can see what the effects are. There are, of course, many more differences. Within the satellites, there's also a difference with the cost. So there are a lot of satellites that are available, have imagery available for free. I know in Brazil you also have access to other ones, but I'm not quite sure what they are in Brazil. Maybe somebody else can add that later. But I know that the American Space Agency and the European Space Agency, they release a lot of satellite images for free. These images usually have a spatial resolution of at least 10 meters. Some of them are sort of larger numbers. And some of the benefits is that they have many different sensors. So you can see, you can get a lot of different information. You also have commercial companies, which might have sub-meter resolution imagery, so it's about 50 centimeters, so it's a lot more detail, and especially good for a city level, but you also need to pay for it. And depending on which spectra you want, the cost is also different. On the other hand, if you have drones, if you really own it, then the cost is more the cost of the drone platform and the training and the operational costs. But you don't need to pay an external company unless the external company is flying the drone. And then the detail that you can get is really 4 to 10 centimeters usually, depending on how high you're flying and the characteristics of the sensor that you have. You can also switch the sensor on the drone to obtain different type of information. So examples of data sets or information from satellite imagery that is available for free are some of the examples that I showed before. So these global footprint layers, a global forest watch, and I wanted to show another application that was done by a colleague of mine, Lorraine. She did her MSc at ITC, did extremely well on her thesis, and she's now working on a PhD also with us. And she looked at how to use unsupervised machine learning and open data to see how the deprived areas in Sao Paulo are different. So to see what the variability is between the slum areas. So the idea is that so she looked at which open data is available. That is a combination of imagery. So again here the Landsat and Sentinel are different image data sets or satellite images that are available for free. Certain data sets that have already been processed. So for example the world settlement footprint. OpenStreetMap, which is like a global, it is a community-driven cartographic database. And then many other indicators, also a globally available digital elevation model, etc. So what she did is first she looked at, okay, what kind of open data do we have available? And there's a very long list here of all these different characteristics that can be related to the socioeconomic status of a slum area. And she did an unsupervised clustering. So essentially what this does is it looks at all the different factors in the different areas of the city, and you try to group them. And she found, for example, 4 different clusters that represent different types of favela characteristics, so like kind of different types of groups. So the one at the top, the numbers don't really mean anything, it's just that there are 4 different clusters and it can be a different one each time that you run it. But okay, then there are some favelas that are very dense and have been there for a very long time. There are some that have less deprivation characteristics, so perhaps a better access to services and are connected to non-residential areas. And there are others which are recently under development, where the slums are recently settling. So she also presented this work to somebody at the government of Sao Paulo, but I forgot exactly which unit. but there was a lot of interest for it, and together with some colleagues she also worked towards making an application on Google Earth Engine where you can run it and you can update it. If there's time after the presentation, I have it open so I can also show how it works. But this is another example of then moving more towards a city scale, what you can do with Earth observation. So what about more detail? Here's some data that we got from a drone. This is from my own PhD work, so the example is from Rwanda. And so when you fly a drone, you get the 3D information through point clouds, which you can turn into an elevation model. And you can get 2D information through orthomosaic. You get both products when you fly a drone. This is important to realize because many people who use a drone, they only look at the orthophoto, but actually the 3D information can also be very helpful. As you can see here, there's a lot of detail. You can actually see the detail in the drainage, for example, which can also provide very important information. And if you look at the added detail that's in the orthophoto to the left, here we got a spatial resolution of 4 centimeters, so it's not flying very high, it was really 4 centimeters. And you can see a lot of detail. You can really see the different types of roofing material. You can see, even at the top right, you can see the structure of a very thin wall, which is not very thick, but that also turns up in the 3D model. So you can actually see the walls and the barriers. And you can also see things such as the sandbags here. So you can see that there are a lot of problems with drainage in this area. And here you can see some steps and some sandbags where the residents were trying to protect the areas against flooding. So there's a lot of very detailed information that you can see in the drone imagery as well. At the time we worked with the city because in this area they were planning an upgrading project. So they really wanted to introduce new infrastructure to increase the quality of life of the people living there. One of the things they wanted to do, for example, was to build a new road. And what was really nice is that while we were taking the drone flights, because they were in the process of designing this, we could actually see how it was used. So they said, first of all, that having the drone images available really helped speed up the field verification. Because at the top left image, that is the image that they had available before the drone flights. It was 5 years older, it wasn't up to date, the resolution was not as good. Whereas if you look at the top right, this was the image from the drone that we took. So you can see that even before going to the field, because you're going to a place that's unknown, that has not been documented, it's informal, it just came up, you can be more prepared because you can see before you go what to expect. They also said it was easier to navigate because you could see where to go. There's also new information. So for example, in the drone imagery at this detail, you can see things such as solid waste, which you cannot see in satellite imagery. And they also said it was very useful to communicate interventions with the community. So they printed the drone image, that's what you see in the bottom left, that the drone image was printed, they went to the communities, they were talking with the communities to say, like, okay, this is what we are planning. And that really helped with the communities because especially when you are improving a slum area, if you want to bring in, for example, a road with better access so that the services can also enter the favela, you will always need to remove some houses. And so they said that it was also, it helped to design better interventions, and it also helped to communicate, that you could talk with people and say, like, look, this house needs to move because this is where the road needs to go. So here we see the drone image, and then part of the work that I did was looking at how to use AI to process it. So we did a classification of buildings, vegetation, and ground. In this case, we achieved an accuracy of above 90% by combining the 2D and the 3D data. And so one of the, but there's a lot more that we can do. So in the previous one, you could see the classification of kind of some large categories like building and vegetation and ground. But I think one of the very interesting things is that if you look in the drone imagery, you have so much detail, you can actually collect more things. So for example, in the left, you can see the yellow canisters, which indicate a water point. In the middle, you can see where there are problems on the street, that the drainage is uncovered, which could be a threat. And then to the right, again, you can see actual drainage. This is from the drone imagery, zooming into the drone imagery, that you can really see the sandbags and drainage emerging. I also said that you can put other sensors on the drone. Some other work that we did with the World Bank in Africa was to use a LiDAR drone, so with laser scanning. And this was for a project in Dar es Salaam where there was a lot of flooding in the middle of the city, and they There's also some mangroves in the floodplain and different vegetation. So they wanted to fly a LiDAR drone to get a very detailed elevation model. And so you have different sensors that you can put on. And afterwards, you can also integrate this data with other like tabular data, socioeconomic data that's available. So to present some of the work that was done by another colleague, a PhD candidate, Cassandra, she's also Brazilian. And she's now working at ITC to look at the relationship of waters, sanitation and hygiene in schools, and how this was affected by the COVID pandemic and what the response was. And then also one of the next things that she wanted to do is, so she's looking at the regional inequality of access to these services in Brazil. And then she's also looking at, for example, what the main factors are. So you can also integrate then the like remote sensing data with social data that is available, or access to services, which is sometimes not visible in data. So I said I would talk a bit about responsible AI and what that means and why it's important. So for those of you, I wasn't quite sure if many of you have been doing machine learning before, but so some of the basics of machine learning, this is a typical example of a machine learning pipeline also from before deep learning. That one is slightly different, where essentially you have the input data, so it could be the 2D data, it could be the 3D data. From the data you get what we call different features or attributes, which describe different characteristics of the data. So the most obvious one, if you take an image, is then the color would enter, but you can also do things such as vegetation index, you can do different texture features. From the 3D features you can also get a lot of different characteristics such as a planarity and things like that. So essentially you would describe which features different dimensions of the data, which you use as input. Then you have the training samples, where you need to define for each class, so for example for here buildings in the top row, vegetation, and ground at the bottom, you need to show examples of what they look like. And in this case it's important that for each class that you want to identify, you need to have examples, and you should also have examples that show how they appear differently. So you need to show also the distribution of what it might look like. And then by combining the training samples and the features, then the algorithm will essentially look for patterns. And then once it's trained, you can apply it to the entire area to get a map. One of the differences with deep learning is that essentially the features and the algorithm are combined. So that process is done automatically, that you just give the image, you give the training samples, and then the algorithm retrain. So AI after 2014, which is kind of when the landmark paper which kind of started the whole deep learning or computer vision was released, you can see that it made a huge impact on the field of Earth observation. So computer vision deep learning is done a lot in our field as well. Here we can see the number of academic publications per year that are related to artificial intelligence and then Earth observation, remote sensing or geospatial data, so specifically also deep learning. You can see that there's really a huge increase in the number of publications that use these algorithms, but also relatively speaking. So if we look at the proportion of publications per year that involve deep learning, you can also see that it went from virtually non-existent in 2014 up to about 10% of the publications now already use deep learning. So our whole field uses deep learning. And yet, when we think of computer vision for different applications in the media, we also hear a lot of concerns, right? So there are facial recognition algorithms that don't work as well from people for different countries. There are like resume or job application searches that are biased against women. And so there's also a lot of guidelines and frameworks that are emerging that say, okay, artificial intelligence is good, yes, we are using it a lot, but what conditions should we be using it under? And then these different guidelines are saying, okay, we should respect the privacy of people, we should do accountability, and there are many different values that are now emerging by different companies, by institutes, by governments increasingly, that are trying to guide how AI is going to be developed in a responsible way. I myself am looking more at the fairness, non-discrimination component and the explainability component in my research. So if we look at fairness and non-discrimination, essentially people are talking about bias. So when an algorithm learns to distinguish, you always need to do a simplification. But one of the issues of bias is really when you can see that there's a consistent difference in the outcome of a classification that is inappropriate. So it's an inappropriate socio-technical bias that is then being confirmed by the algorithm. There's this documentary, I know it's on Netflix in Europe, I don't know if it's also on Netflix in Brazil, that talks about this in different fields. I'll skip over that one, because I'm going a bit slower than I expected. But this is an example of what bias looks like in geospatial applications. Because one of the questions is that because we are not dealing with personal identities when we look at the building and we are mapping, what could biases look like? So here, this is again of Dar es Salaam. On the left, you can see the results of a community manual mapping, where they went and they digitized manually over the area. And to the right, you can see the results, or these were building footprints that were released by Microsoft, where they use AI over the entire country. And they said, okay, we have building footprints of the entire country. But when you zoom in to a certain area, you can see that the AI algorithm actually missed a lot of the buildings in the middle. And these buildings are actually the ones that are located, I mean, if you see it from an image, it's very typical for an informal area, or where the people are more vulnerable, of a vulnerable community. So what's very important is that as we are using AI, that we are very conscious of what these differences might be, because this is, for me, what biases will be in geospatial algorithms. Because if I see that even something as simple as a building data set is consistently worse in vulnerable communities than, for example, here the bigger buildings, which would be more formal areas, good, then what if we use this for to plan a flood mitigation measure, right? Then essentially you don't see the buildings of the people who need protection the most. So again, this is not, this is just an example. It is not a consistent evaluation of this data set, but I think it speaks very clearly to why we also need to think of biases in our domain. So the other thing I look at is explainable AI. Explainable AI is essentially that deep learning is a very complex method, and many people don't want to use it because they don't understand what's going on. And especially decision makers will say, I cannot use the output of a deep learning algorithm because I don't know if I can trust it, I don't know if it's reaching a decision or not. So the idea of explainable AI is to make this clearer. And there are four main reasons why people do this. First of all is to control what the algorithm is doing. The second one is to improve the algorithm, because if you see where it's going wrong, you can also improve it. You can also discover new things. So when you understand what the algorithm is prioritizing as being the most characteristic of a certain class, it might be something that you did not think of before. And sometimes also to justify why a decision was made. So you really want to look for one specific example, you try to explain why this decision was taken. In our field, so this graph shows the number of publications in our field of Earth observation. And you can see that it's mainly to control what the algorithm is doing. And how do we do this? We can do this by using interpretable models, so really building the model in such a way that it is easier to understand. Some people try incorporating domain knowledge, but it isn't very strong yet. We often do feature selection and importance. It's one of the most commonly named one. And the other one is saliency maps. So I'll give some examples. So here we have an interpretable model. An example from our field where there was a building classification. And then what they did is they added an uncertainty metric to the deep learning algorithm. So they found a way of that during the training, they could get an uncertainty of the prediction. And so the result was not only an outward map of building classification like you see in the middle, but also like to the right that you could see a certain degree of confidence in the result. So that should be able to tell somebody, like, okay, in this case, if there's more confidence or less confidence in the result of the classification. One that is essentially best practice in machine learning, always when you do a supervised classification, is feature selection or importance. So in the workflow before, I said, okay, you can incorporate 2D data, 3D data, color, texture, things from other sensors. You can, when you do a classification, you can take the same image but at different timestamps, especially for vegetation, that's often done, so you can see how things are changing during the year, because that will help with the classification. And feature selection and importance essentially says, out of all of the features that we have, also remember the table I showed from Lorraine's work, there are often really a lot of features that we work with. Which ones are the most important? And that says something about, that can explain why the model took certain decisions. And it also induces sparsity. So if you see that only out of the whole table, imagine that only 10 turn out to be important, then you also know I need to collect next time I don't need to collect as much data, because if I have only 10 features for the input, then it also gets a high classification. So feature selection importance we do a lot. I think almost half the publications that said they did something about an explainable and interpretable model use that. And then another one that is coming up in computer vision is what they call saliency maps. And here's an example of a student of mine who looked at street view images in slums in different areas of Jakarta, and essentially used the saliency maps to understand what the difference was between street view images taken from a slum area and street view images taken from a non-slum area, with the idea that maybe there are certain objects that also help differentiate between the two. And then the idea of a saliency map is that for all of these images that turned out to be classified as slum, the redder parts of the image were more important for the algorithm to reach its decision. And these types of maps, so the idea is that if ideally this would be highlighting certain parts of the image that are very typical for slum areas. In practice, the saliency maps, even though for this type of algorithm they're one of the most common ones that's out there, there are also a lot of critiques about it, because this example is from a different publication where they trained an algorithm to recognize huskies. And there they said, okay, if you try to explain why it is a husky or why it is a flute, the musical instrument, essentially the same part of the image is highlighted. So you don't always understand why this part of the image was highlighted, and it doesn't tell you either what to do to improve it if there's a wrong classification. So that's a work in progress to find better ways of explaining that. Another critique is that we often use random forests in remote sensing. That's a different type of classification technique, where essentially if you would have one tree, you take binary steps each time. So if you have all of your input data, you look at one thing first. So for example, if you look at the drone image, you say, okay, is it, or let's say that you have 2D and 3D data, you might look at the elevation first and you say, okay, if the object is more than above 2 meters high, then it's either a tree or a building. If it's not, then it's something on the ground, let's say, or something lower. And then you say, okay, so you have one decision, just elevation. Then you move the samples to the next part, and then you have another decision. You can say, okay, if it's green, then it's a tree. If it's not, so if it's 2 meters high but it isn't green, then it's a building. So essentially a decision tree will look at that. It looks at one feature one by one, and it divides your group so that at the bottom, you all have samples that represent the different classes. So in a way, it sounds interpretable. The problem is that when we use random forests, typically in Earth observation, we don't have just one, but you train hundreds of these trees. So even though you could theoretically go back and feature by feature understand why the model got to this decision, it's actually very difficult because there are hundreds of them. So as a human, still we are not really going to understand what's going on, even though we can trace it back. So this is one of the differences between Earth observation scientists and social scientists, because in Earth observation we are sometimes used to saying like, oh, I'm using an interpretable model because it's random forest, but then the social scientists are telling us, okay, yeah, actually it's not. So it's really something important in our field that as we are using more and more machine learning, that we also look at what these other factors are saying. When society is saying that we need to do responsible AI, or what the social scientists are saying, like, okay, your method doesn't really work because humans are not understanding. To take all of these things into account, to also select which things we want to keep on investigating. Another critique is that methods are too expert focused, and that it's difficult to understand when you can use a model. So often in our field, when we look at explainable AI, we only try explaining the algorithm, but it doesn't say something about the entire process. So as a model can be very specific to be used in one place, you also need to be able to learn, and that's one thing that they want to do through what they call data sheets and model cards, to describe better how the model was trained, which data was used, so that somebody who looks at the model will also understand how it can be used, because a model trained for one place, it does not always work well in a different place. So there's also a lot of work that's under development, and also, for example, in Europe, they're really making legislation that says each model or high-risk model of AI developed on the European market or deployed in the European market needs to have a clear description of how and when it should be used or not. So people are comparing it to this nutrition fact like you sometimes find on the food, right? This is something about when it was made, and this is something that's really standardized. And now there is some research going on to say like, okay, how can we do that for models so that also it's very clear to somebody like, okay, I can use this or I cannot use this for a specific application. So to wrap it up, Earth observation is very useful to support the Sustainable Development Goals. It has many different characteristics. Like I said before, it can be regularly updated, it's comparable, it goes back in time. So really having this objective view of the surface of Earth over time and over different places really helps support the monitoring of the Sustainable Development Goals and the implementation of different Sustainable Development projects. Also that if we look at satellites and drones, which are some of the two most common tools that we have in Earth observation, they have different characteristics and so also best used in different ways. And also that AI is definitely making an impact, or has made an impact on our field already. But also as we move forward, we need to be aware of the different critiques that there are about it, so that we can develop it in a better way. So a couple more things. I put the references of all of the colleagues who contributed to the presentation with the different projects. I was also asked to share the information that we now have a UAV or a drone center at ITC, which is quite new, where we also do a lot of research and a lot of projects. So also feel free to reach out and to ask questions about that. And with that, I'd like to wrap it up and hear your questions.
Any questions? Perguntas? Se quiser perguntar em português, a gente pode fazer a ponte.
Eu queria perguntar assim, como que ela vê a questão, por exemplo, dessas novas ferramentas como o segment editing do metaverse e como isso pode impactar nesse contexto de ter uso sustentável, enfim, dessas ferramentas a partir pensando que isso está sendo proposto por essas grandes companhias.
So to use the segment anything model, how that influences?
Yes, how do you see the...
No, I mean, it's like I said, I think one of the things is that there's not enough, we're always focusing on the same questions. So, okay, building detection, everybody does building detection, but if we actually look at the image, there are a lot more things that are interesting. Also this week we were talking about, like, okay, what can we see, what would we want to detect? And the segment anything model, it can really speed up the generation of the training data also. So in that way, it can really speed up the whole workflow of the classification, because I think one of the reasons that machine learning is not used as much in practice yet, or as much as it could be, is because just setting up the workflow takes a lot of time. So segment anything can really speed that up.
Mais alguém?
Can I ask something? Thank you. I work with groundwater, and I was imagining if there is something that we can do to study groundwater recharge in urbanized areas with drones.
Yeah. So groundwater recharge you will know better than me, but from my understanding, it has to do with impervious surfaces. So from what I remember from my bachelor, it said it has to do so indeed with, so you would need to know how much of the surfaces are impervious. And also for the pervious surfaces, it has to do with the slope also, right? Where there's water retention. So again, it's not my expertise, but what I would imagine is that then by looking at the image, you can classify these are impervious surfaces that the water does not pass, and then these are the ones that's, for example, open dirt or open terrain where it could go in. And that also by having a much more detailed elevation model, you may be able to identify the water retention better. The thing is, it would work better in arid areas than if you think of places like you're looking at Sao Paulo where there are trees everywhere. Because of course the problem is that if you have it under a tree, you will have difficulties both seeing and also getting a good elevation model. If there are any other aspects of groundwater recharge, please do let me know, because I'm trying to remember what the important factors were.
We can have groundwater recharge through leaking of the pipes that for supply water or sewage.
Yeah.
So we can also have this kind, not only from
Maybe.
percolating water.
Okay.
So my question was about also if you have some kind of equipment that we can put on a drone to do some kind of geophysics in the area and see the humidity on soil or something like that.
So humidity, I mean, with remote sensing, you look at the satellites, no? You look at the emission. It's a different wavelength. I don't know. I have not heard of projects doing that with drones, but I'm not sure if there are. Yeah. I'm not sure.
Okay, okay, thank you.
Mas nós estávamos discutindo uma parte de identificar vazamento, por exemplo, olhando para o risco, e solo exposto olhando para o risco. Então, né, daria para pensar também do ponto de vista de recarga. Where we have trees, we can use the LiDAR data. So for São Paulo, for example, we have LiDAR coverage for the whole city, so we can combine imagery and
yeah, definitely. I mean, at the city scale, that definitely. I was thinking also that what I remember, because when my bachelor was integrated under water management, so they were talking also a lot about, for example, agriculture and arid environments. And a lot of the measures of slowing down the water to prevent erosion and to increase percolation, sometimes there were smaller measures, from what I remember. I'm guessing that it might be the same now. So for example, that when there was a slope and they built a crop, they built just like small elevations around the crop, so that there the water would stop it a little bit and sink or be retained for a longer time, or vegetation belts, you know, where, to slow the water down. And I think what might be interesting from a drone, I'm not sure in an urban area, because I don't know what measures you are doing, but in a different area, is like for these kind of smaller, or anything that is done more at a community level, it might be easier to identify simply because you have a lot more detail also, the spatial detail that you get.
Because the content of groundwater or the content of water in soil is important to know maybe when will happen some landslide.
Yeah.
Because the saturation, the water saturation in soil is an important thing.
Yeah.
I don't know if you discussed this.
no,
Okay.
we didn't get there.
I know that. So for satellites, have you worked with satellite imagery? Because I do have specific satellites that are for soil moisture.
But in this kind of
Yeah, in this case,
scale.
yeah, that's why I was thinking. But the thing is, so if it's a sensor that they have on the satellite, it could be that there are also applications for drone, but I've not heard of them.
Or radar imagery. Or radar imagery, which is very sensitive to the water content.
It's possible to combine radar data with drones and try to combine everything together, so to assess your problems. No more questions? Okay, so I'd like to thank you a lot again for your time and for being here, and that's it. If we should let
my email's here, so if there are any other questions later, please just send me.
Please get back one slide for us to the
the QR code.
Yeah, of course. This one.
Yes.
Does it work?
Let's see. Yes.
I have a very nice colleague who's like, we have the new UAV center, you need to tell them about the UAV center. They're also working with UAV, so I said, okay, here's his side. Is it not working?
Yes.
Okay.